go. All right, so let's do this classification task using the MNIST data set. So I'm using Google Colab again, and wonder if there's a paste button up here. I think there is. No, that's something else. All right, I have to use the keyboard. Haven't figured out how to expect me to paste into there. So this will fetch the data from the OpenML library. And this will give us information about the shape of the data. While that's running, I can be readying the next one. We can add another block of code here. But I'm not going to run it until the previous one is done. And the little green arrow tells you which step is running. All right, it took a while. Then it's just giving me some information about the database. And so here's how it looks. It is a grid of numbers, and all the ones I'm seeing are zeros because the edges of the image are black. But inside here, the numbers that skipped will include the colors that are greater than black. And here's a summary of the shape of the entire database. So it is 70,000 times 784. There are 70,000 images, and each image has 784 pixels. And the Y is the labels. So there are 70,000 labels, which is the right answer for each of those images. And you can view some of the images by just bringing in a Python plotting library. And this will print, I think, 10 by 10 of them. There you go. So you see 100 examples of the images. You get a pretty good idea what you're dealing with here. This is kind of interesting. You've got a sort of defect on the edge of this one, which would probably confuse it and make it think maybe it was a 7 or a 9. Anyway, they got quite a lot of variation. So you can split it into training and test sets using 60,000 images to train and leaving 10,000 that the model has not seen to test it on. And now I'm going to reduce it from a multi-category task into a binary task by just calculating labels of whether they're a 5 or not a 5. So this is going to be true for all the 5s and false for all the other digits, and the other part is going to be the test set. So you have 5,000 that are true and 50,000 that are false. So that's the situation. And here's how we make a simple stochastic gradient descent classifier, which is the technique we've talked about. We just make the font smaller in that window to get it to fit better on the screen. There we go. And this will give me the prediction for the first 3 images, just so I can get some idea how it works. So as it runs, it imports this, and here it is doing the fit, and that's training it. And as you can see, the epochs are going by, just like our previous stochastic gradient descent. It's making a bunch of little steps, and you can see the loss going down. That's the number of images that were incorrectly classified, going down as it improves. And I didn't tell it how many steps to make, so I think this one is going to use automatic termination. And for stochastic gradient descent, what you do is you keep going as long as the loss is improving, but as soon as it gets worse, then you stop. And I think we're going to see that here. It's starting to bounce around a bit. So it made some decision that it's not really getting any better, and it stopped. That's when you know you've hit the bottom. And so now it makes predictions, and it correctly recognized that the first one was a 5, and it correctly noticed that the next 2 were not 5s. So that's fine. And this is how you do the cross-validation. It's all built into the library. So this is going to retrain the classifier 3 times using only 2/3 of the data and evaluating on the 1/3 of the data left behind. So we're going to see 3 lists of epochs go by. And this one here got the loss down to 77, which I think that means 77 total images incorrectly identified, but I'm not entirely sure what the scale is. And see, it finished the first one, got it down to 157. And then it's going to train the second classifier. And it down to 155. And the third classifier, and these numbers are bigger, but that's because there's more total images in the test set, I think, this way. And the third one's getting down to about 202. Okay, so it's done. And here's the result, 95% right, 96% right, 96% right. So those are the three cross-validation scores to see how good your image is. A typo in the instructions. Yeah, 10,000. You're right. That should be test set. Thank you. Good. Thanks for pointing out the typo. All right. So anyway, you can calculate these things. You can get the confusion matrix that shows you the true on the diagonal and the false here. You can get these other graphs. I don't think I'll keep doing them live. It's pretty simple. Here you can see, however, the neuron output, which will help understand this. So this is the decision function for the first 12 images. And so you see this one is really a 5, so the output is 2000. This is not a 5, so the output is negative. And here's another 5. And so by default, you put the, it chooses a threshold near 0. So signals above 0 are considered 5 and below 0 are considered not 5. And you can see there's strength in the output. So it could give you a measure of confidence. Like this one, you're very confident it's not a 5 with minus 13,000. These ones here at minus 2,000, you could say you're not that confident that it's not a 5. And you can vary the threshold value and get this chart and see how that goes. And you can, there's a few flags to find. And then you can do the multi-classification that sorts into all 10 categories and compare the various outputs there. So this is good to see how these multi-class classifiers are built. And all right. I don't think I'll bother with the details. You get the confusion matrix and so on. And there's a few flags to find there. So give it a try. The main point of this one is to understand how you make a binary classifier, how you make a multi-class classifier out of it, and how you evaluate these things to get some kind of measure of their performance. So I'm going to stop this video.